Okay guys, let's take a look at today's lesson. This is Vectors Day 2. This marks the end of our work with parametrics and vectors. We'll move into polar tomorrow. And today's lesson really requires a calculator, so I hope that you brought one with you. You will definitely need one for the daily work. And I'll be doing a little bit of calculator stuff up here. Alright. This is a typical question prompt on the AP test for a free response question. We have 2 calculator free responses on the AP test and 4 non-calculator free responses. This would be similar to a calculator free response. And so you'll notice that they ask a lot of different questions about the same prompt. So that's a typical pattern of the way that the free responses look. So we have a particle moving along a curve in an xy plane and has this position of x of t, y of t at time t with, and we're given 2 derivatives. We're told dx dt is sine t cubed and dy dt is cosine t squared. We're also given another piece of information. At time t equals 2, the object is at the position of 7, 4. So that's the information that we're given for this problem. Alright, so let's write the equation of the tangent line to the curve at the point where t equals 2. So just recalling, we've done lots of tangent lines. We need what piece of information to write tangent lines? We need point and a slope, right? We need a point and a slope. And they, were very kind to give us, we have the point, 7, 4, so we don't have to go looking for it, luckily, because we don't have a position function. We have the point, and we need the slope. So to get the slope, we need the dy dx. We don't have that, but it would be easy to create, right? Because I have already dy dt and dx dt, so I just make a fraction of those and do dy dx is going to be cosine t squared over sine t cubed. Okay, so that would be my derivative. And we want to evaluate the derivative at 2, so we would substitute a 2 in, cosine 2 squared over sine 2 cubed. And this would, definitely be a calculator problem. Hopefully nobody in here would want to try to do that by hand. It's really not a unit circle value. So we would put that in our calculator, and it would generate now a number for us. Now, one thing I want to caution us on, really important that you're in radian mode. Some of us are just accustomed to trusting that we're in the right mode and not checking. You're going to get a wrong answer if you're in degree mode. So just please be sure you're in radian mode when we're dealing with trig functions like this. All right, so we put that in our calculator and we get negative 0.66067. So that would be our slope. And so we're ready to write our tangent line equation. So we do y minus y1. So y minus, here's our y1, which is 4, equals m, which is our slope, negative 0.661 times x minus x1, and our x1 is 7. And so that gives us our tangent line. Okay, pretty straightforward, just with a calculator. I mean, nothing really shockingly new here. Part B asks us to find the speed of the particle at t equals 2. Okay, so we would think back to our formulas from yesterday. The formula for speed, if you recall, is a radical, right, with the dx dt squared plus dy dt squared. It's just a radical for speed. Arc length has the integration sign in front of it. We're just talking about, we're talking about speed or magnitude, the magnitude of the velocity vector. So we need to find the derivative at 2. So we know what the derivative is. So let's find, we need dx dt at 2, which would be sine of 2 cubed, which is 0.98935. Then we need dy dt at 2, which would be cosine of 2 squared, which ends up being negative 0.65364. Okay, so here's our two values. That is our dy dt at 2 and dx dt at 2. So using our formula for speed, we want to do the magnitude here. Now let's talk about a little bit of shortcut, I guess, when we're working on the AP test. The seconds matter. So instead of rewriting these big numbers, what they allow you to do and I allow you to do is label it. Call that A and call that B. And then in my formula, I just need to write a squared plus b squared instead of those big weird numbers. Now, I would encourage you to store the numbers so that when you, for a couple of reasons. If you store them like this, then they're accurate and you don't have to worry about misentering them, re-entering them. And also, you won't have to worry about missing the accuracy. They want you accurate to the thousandth. If you're even 1,000th off, you lose the point. And you know how to do this work. I don't want you to lose a point because you don't round properly. So you can always go farther than 1,000th, unless it specifies. But the default is 1,000th. So we don't want to round before the final step. So when we put that in our calculator, we will get 1.1857. Which you can leave like that, or you could round or truncate at the thousandths. Either way. Yes, ma'am. Only because they didn't give us. So if they don't give you any units, you don't have to do the mystery unit per seconds or anything. You just don't have to give it at all. But many times they will give you a unit. Mm-hmm. And that's on yes, right. They don't really get bent out of shape about the U. You don't have to do the mystery unit. Only if they give you a unit. If they give you a unit, you definitely have to do the unit. All right. So for part C, it asks us for what value of t, and they're restricting the t value. It needs to be between 0 and 1. Does the tangent line to the curve have a slope of 4? Find the acceleration vector at this time. All right. So here, what I would do is we want a slope of 4. So we want 4 to be equal to our dy dx, right? I think that's pretty clear. Right, slope is 4. So we would say 4 equals, and then our dy dx was cosine t squared over sine t cubed. Okay. The way that I would solve this in my calculator is I would put 4 as y1. I would enter this as y1. I would enter this side as y2. And I would intersect. I would do the intersection of those two quantities. That would give me my t value. There are other ways. There's like a solver on your calculator, but I'm not really comfortable with that. I wouldn't choose that as my first way to do it. This I'm pretty comfortable with, so that's what I would do. That's going to give you a t value, which you should store. And don't store in x. I still have some students wanting to store in x, maybe because it's faster. But x changes as you use the grapher. So really, probably not the best place to store a number. You really want to store it as a alpha A, alpha B, somewhere. Store it somewhere. Don't store it as an x. Unless you just like to live dangerously. If you want to live dangerously, I guess store it as an x, but I wouldn't advise that. So our t value is going to be 0.61648. And we're going to use that for part 2 of this question. This question asks us for the acceleration vector at this time. Now, what I would like to do is, yes, we can do this by hand. We can take the derivative of the first derivative and we can substitute in this number. But I would encourage you to use your calculator for this issue. And I'm going to pull up my calculator and just go through. You probably already know how to do this, but I just want to demonstrate. This portion of the problem, find the acceleration vector at this time. Since it's at a particular time, we are able to utilize our calculator instead of doing all of this by hand. So let me clear out. So if you be sure to write this down, I'm going to have to clear the screen so I can pull the calculator up. So that's the t value that we're going to sub in. All right. so what we would do is we would go to Math 8. That's our derivative. Math 9 is our integral, which we are quite accustomed to. Math 8 we probably haven't used that much. We want to do with respect to x. And our formula is, let's do our dx formula. So sine t cubed. So we would do sine x cubed. And we want the derivative of that at, and now I didn't do it, let's put an extra parenthesis there just to be sure. Okay. So I didn't store that value, but that's what I would do. If I would have stored it like at alpha a, and then I would have written alpha a here. But since I didn't do that portion on the calculator, I'm just going to type in 0.61648, and that gives me my x component of the acceleration vector as 1.109. Much faster than doing the acceleration vector by hand and then subbing in the 0.616 thing. I encourage you to utilize your calculator that way. And then you would do the other one. So that's with respect to x, and that's our, what was it, cosine t squared, cosine x squared. And that's evaluated at 0.61648, and gives me an this would be my y component, my vertical component of negative 0.457. So I would write my I'm not going to try to write on this, it doesn't play well. So I would write, this would be my x component of my acceleration vector, and this would be my y component of my acceleration vector. Is that okay? All right. Well, we need it to be gone. Okay. All right. So let's write, that would be, to finish that, our acceleration vector at 0.616. Okay. Our acceleration vector at 0.616 would be 1.109 and negative 0.457. Okay. d2y. The y component of acceleration is the derivative of the y, the derivative of this, right, with respect to whatever number we have. Okay. So the last part says find the position of the particle at time t equals 1. Another place where you really are have to use your calculator. We cannot integrate sine t cubed by hand. Okay, we can't. We don't have a formula for that. We can't do U substitution. We can't integrate that by hand. So that's the kind of equation you're going to have on the calculator portion, things you can't do by hand, things that are fairly complex. All right, so this is going to take us back to a technique that we learned a month or so ago when we were working with the fundamental theorem of calculus. So to find the position, we need to find x of 1 and y of 1, right? And I don't have x of 1 and y of 1. I don't have the position, so I'm going to have to integrate. So we're going to integrate. So we're going to work on x of 1 first. Okay, to work on x of 1, we're going to integrate. And if you recall from the technique that we learned, we would integrate from like what we knew to what we wanted, or what we wanted to what we knew. Or remember, so what we know is what the position is at time 2. What we want to know is the position at 1. So I'm going to integrate from 1 to 2. Okay, because again, 1 is the one that I want, and 2 I know. It's like my initial condition. I have to use it. Okay, so my x1 is going to be the integral from 1 to 2 of this sine t cubed dt, and that equals x of 2 minus x of 1. You recall that technique where we break it out with the fundamental theorem and then we sub in the numbers? That's what we're doing here. And so we know x of 2. Our x value at 2 is 7. We don't know x of 1. We would substitute this into our calculator. And I actually don't, I did it a different way on here. Would somebody put that in the calculator? Tell me what weird decimal. What is it? 0.218. Okay. So then I solve for x1, and x1 gives me 6.7818. Okay? That's my x component of my position. So let's look at our y component. So same kind of thought process. We're going to go from 1 to 2, and we're going to use our y, which is cosine t squared. And that's going to be y of 2 minus y of 1. Right? Same technique that we used previously. So we know y of 2 is 4 minus y of 1. Again, I'm getting those numbers from here. We know that at time 2, this is our position. That's where I'm getting the y1 and the x1, or the y2 and the x2 from. Okay, and then we do this in our calculator, the integral from 1 to 2 of cosine t squared. Someone have that decimal for me? Negative 0.443. Okay. And so then we solve for y1. So y1 is going to be 4.443. And so our position, we have it, x1 and y1. 6.781, or we can truncate or round. We'll round. 6.782 and 4.443. Okay, how is that? We okay? Notice that the position, I want you to look up here what they wrote. The position is a vector, right? That's what they wrote. We're not going out on a limb here. They said the position is a vector. So I'm writing the position as a vector. Okay? Are we okay?